Hello everyone, welcome to the presentation of our ICML 2025 paper, Interchangeable Token Embeddings for Extendable Vocabulary and Alpha-Equivalence. I would like to start by emphasizing the difference between machine learning and numerical optimization to set the stage. Consider a curve fitting problem with these training samples. I could fit an extremely complex polynomial to these lines yielding a curve like this. This would be perfectly fine if this weren't a machine learning problem, because it fits the given points perfectly. However, the learned curve does not reflect the underlying distribution of the given points, which is much simpler. When we evaluate the model outside the training distribution, the model's prediction will be completely incorrect. This shows that the intention to generalize to out-of-distribution samples is what separates machine learning from pure numerical optimization. However, we don't have to restrict ourselves to samples that have the same structure. In other words, generalization is not limited to the input content. We can also generalize to different input structures. For example, we could expect an image model to generalize to larger images after training. Or we may want a graph neural network to generalize to different graph structures than those seen during training. It is important to note here that, unlike other forms of generalization, structured generalization requires architectural changes, because if the network is not designed with structured generalization in mind, it won't even be able to accept such inputs, let alone generalize to them. For example, an image model designed for a constant image size cannot even take larger images as input. Now we will take a look at a machine learning problem and identify a new form of structured generalization. This problem involves propositional logic. First, we have the constant true represented by capital T. We also have atomic propositions, denoted by lowercase letters. They can be either true or false. Then we have two essential operators, with the first one being the negation operator and the second one being the conjunction, also known as the AND operator. With these operators, we unlock all logical operators because the rest can be derived from these. But we won't go into further details here. The problem we are trying to solve here is assignment prediction. Given a logic formula, we want to assign values to propositions such that the formula evaluates to true. There is also an extension of propositional logic called linear temporal logic. Instead of reasoning about constant propositions, we consider propositions that change over time. By default, propositions refer to the current time step. To refer to the future time steps, we introduce a new operator called next, which asserts that the given statement holds in the next time step. For more complex changes, we introduce the until operator, which denotes that the left operand holds until the second operand holds. Our goal in LTL is still the same as in assignment prediction, but since propositions change over time, we call these assignments traces. Thus, the objective is called trace generation. Previously, deep learning methods were utilized on these problems to address the scalability concerns. The pioneering work was called DeepLTL. Interestingly, this method can generalize to longer formulas not seen during training, thanks to the tree-based positional encoding method. Here we see that the DeepLTL model was trained on formulas with a maximum length of 35 and produces mostly correct predictions, which are denoted by green. But it can also handle longer formulas, up to 50 tokens. This is an example of structured generalization, but there is another type of structured generalization in this domain that has been neglected in the literature. Consider a formal expression like this. Here we can rename the bound variables without changing the meaning of the expression. For example, instead of a and b, we could use x and y. This concept is called alpha-equivalence. Regardless of how we name the variables, the function has the same meaning. Alpha-equivalence is not specific to this domain. It emerges in many formal languages, including programming languages such as Python. For example, consider a Python function like this, taking a and b as parameters. Here is the same function with different variable names, x and y, but it's still functionally equivalent to the previous one. This demonstrates the concept of alpha-equivalence. Based on this concept, there are several desirable properties for formal language models. First, we would like to enforce alpha-equivalence so that changing variable names does not change how the model processes the input. Secondly, we want to enable generalization across tokens. Since all variables share the same underlying concept, a model trained on 3 variables should generalize to more variables without additional training. In the next section, we will see how the proposed method tackles this problem. Here's an embedding matrix that converts tokens to vectors in a language model. Rows represent tokens and the columns are the dimensions of the embedding vectors. The last 3 tokens are subject to alpha-equivalence. We call these interchangeable tokens. Here's how we modify the embedding matrix in our method. Interchangeable token embeddings have 2 parts. The first one contains learnable parameters that are shared across interchangeable tokens. The second part, on the other hand, is not learnable. It features randomly generated vectors which make the embeddings distinguishable from each other. During training, this second part will be randomized for each forward pass, forcing the model to distinguish variables without learnable parameters. This embedding strategy enables generalization across interchangeable tokens. Suppose that 2 new tokens are added during test time. We extend the first part since all learnable parameters are shared in that region. And since the second part is not learnable, we can simply generate it randomly as before. Now, the embedding matrix is extended without any additional training. To make this method work within a transformer encoder-decoder, we use 3-way weight tying. Since some parts of the embedding matrix is manually built in the proposed method, we need to tie these parameters. This will ensure that both the encoder and decoder use the same embedding matrix. It will also make sure that the input embeddings are consistent with the output embedding space, which is determined by the final linear layer in the network. Let's go back to the embedding matrix. In the next section, we will take a look at how the random part is generated. For simplicity, random vectors will be visualized in this 2D space. The first method is also the most straightforward one, normal distribution. Here, we simply take a sample for each dimension from the normal distribution. The second method is called neighboring points, and it uses a discrete sampling set, unlike the normal distribution. For each dimension, we take a sample from the set containing -1, 0, and 1, while ensuring that the resulting vector is not completely 0. In normal distribution, the probability of sampling the same vector twice was negligible. But since the sampling set is discrete here, we need to make sure that there is no collision between sampled vectors. The next method is called hypercube vertices, which is also a discrete method, but this time each dimension is sampled from the set of -1 and 1. This also naturally ensures that the resulting vector is never 0. As the name implies, these points form the vertices of an n-dimensional hypercube, which corresponds to a square in this 2D space. And the resulting vectors look like this. Next, we will take a look at normalization techniques in the proposed method. We will investigate how these parts are normalized. We apply normalization for each row separately, thus we will focus on only one row. In the first step, we separate these parts and normalize each of them independently. This ensures that neither part overpowers the other one. Then we concatenate these parts again and normalize the row as a whole. Our reasoning here is that this further improves the gradient flow. Now that the matrix is normalized, let's turn our attention to how the logits are calculated. Logit calculation happens in the final linear layer, which is the same as this embedding matrix due to weight tying. Given a feature vector v, the logit calculation looks like this. It's simply the dot product between this matrix denoted by u and the feature vector v. Now let's focus on a single token. We take a single row from the embedding matrix. Since this is a dot product between 2 vectors, we can write it like this. Here, theta is the angle between 2 vectors. And since each row is normalized, the first term here disappears. The dot product boils down to the length of v multiplied by cosine of theta. This observation leads us to feature normalization. What if we normalize the feature vector in addition to the embedding? The only thing that remains from the dot product is the cosine term. In literature, this is known as cosine loss, which was frequently used in face recognition, but to the best of our knowledge, it was never used in a language modeling context as we did here. One of the disadvantages of cosine loss is that it is sensitive to hyperparameters. To address this issue, we apply a cos loss function, which scales this cosine term adaptively throughout training. Before we move on to the experiments, let me explain the baselines we considered. The first one is the naive baseline, which uses traditional embeddings without any modifications. Naturally, this baseline fails to generalize to larger vocabularies. The second one is called full vocabulary baseline. It also uses traditional embeddings, but it sidesteps the vocabulary generalization challenge by using a training dataset with a larger vocabulary. The final baseline is alpha-dynamic baseline. Unlike other baselines, this one can actually generalize similarly to our method. Let's dive into its details. Here is the default embedding matrix. In this baseline, we extend the embedding matrix with test-only tokens before training. Unlike our method, all of these are learnable parameters. To ensure that the model learns all tokens, we shuffle these embeddings in each forward pass. This is equivalent to augmenting the training dataset by renaming variables. Next, we will take a look at the experiments. We created a new variant of the copying task that involves vocabulary extensions. But I won't go into the details of this task in this presentation because solving this task is trivial when the model is sufficiently large. All models achieve perfect performance on this task, except for the naive baseline. We also tested our method on two logic tasks, linear temporal logic and proposition logic. We will start with the experiments in linear temporal logic. We will plot the experimental results on this graph. Here is a sample from the dataset taken from the pointed location. The x-axis represents the formula length. Moving right makes the formula longer without affecting the variable count, which is determined by the y-axis. Moving down in this graph increases the variable count without affecting the formula length. To denote the sample count, we interpolate the brightness of each cell. White represents 100 samples and black represents 0 samples. This rectangle denotes the limits of the training dataset. The model is expected to generalize in terms of both formula length and vocabulary size. These are the results from the baseline model. Although modern positional encodings allow length generalization, the model cannot handle larger vocabularies. As a result, the overall accuracy is only about 42%. On the other hand, our embedding method enables vocabulary generalization and combines well with generalizable positional encodings, achieving an overall accuracy of approximately 91%. In fact, our method almost matches the performance of the full vocabulary baseline model that has been trained on all variables. Here, the training dataset for the baseline was extended, but its accuracy is only a few percentage points above our model. Finally, we have the alpha-dynamic baseline. Despite being the only baseline that can generalize to larger vocabularies, the overall accuracy of this approach is approximately 8 percentage points lower than our method. We have seen that the full vocabulary is the only baseline that outperforms the proposed method, but it's much more expensive to generate a full vocabulary training dataset. Here we plot the relative time to generate a single sample for the LTL task. This shows that generating a sample becomes significantly more difficult as the formula gets longer or contains more atomic propositions. Even if we keep the formula length constant, increasing the vocabulary size requires a lot more compute. This provides motivation for vocabulary generalization because larger vocabulary samples are harder to find. Next, we will look at the experiments in proposition logic. But before the experimental results, I will emphasize the difference between these two tasks. In the LTL task, we have the fundamental logic operators in addition to the temporal operators. Here, temporal reasoning presents a challenge. In proposition logic, on the other hand, we don't have a temporal dimension. However, we have several derived operators, which allow us to express more complicated formulas without making the formula longer. Here are the results for the proposition logic task. The overall ranking remains the same. The full vocabulary baseline is the best, followed by the proposed method. Alpha-dynamic baseline is ranked third, and the naive baseline is the worst model. For comparison, here are the results for the LTL task. Overall, the performance differences between methods are more pronounced in the proposition logic task. To put these results into perspective, we evaluated the performance of a general-purpose language model on these tasks. We used the 3 billion parameter version of Llama 3.2. It's a small model by LLM standards, but it's still 3 orders of magnitude larger than our specialized models. Despite this, it performs worse than all of them, even the naive baseline model. This shows that specialized models are still valuable for niche application areas such as formal logic. Now, we will take a look at the ablation experiments in both logic problems. Here, we disable one feature at a time, except for the row normalization, because we cannot use ADACOS when row normalization is disabled. These results show that part normalization is absolutely necessary. However, the impact of ADACOS and row normalization depends on the task. They deliver a considerable improvement on the LTL task, but there is no significant difference in the proposition logic task. Now, we will investigate the Alpha-Covariance results, which is a new metric we developed. The goal here is to measure the model's sensitivity against alpha convergence. An alpha convergence is a transformation that generates an alpha-equivalent expression. Suppose that we have an input formula like this, and the vocabulary we consider is A, B, C, D, E. First, we generate all alpha-equivalent variations of the given input formula with this vocabulary. We denote the resulting set using P. Next, we generate the model's predictions for all of these variations. After that, we undo these alpha conversions and collect the results in a set, which is denoted by U. Ideally, the size of this set should be 1, because regardless of how we name the variables, the model should give the same semantically equivalent output. Therefore, we formulate alpha covariance like this. If the size of U is 1, alpha covariance is 1, which is the most desirable outcome. The opposite of this case is when the model gives a different answer to each alpha equivalent input. In that case, the size of U will be equal to the size of P and alpha covariance will be 0, representing the worst outcome. Here are the alpha covariance results from the previous generalization experiments. We only consider 1200 alpha equivalence variations for each sample here because 10 factorial is a huge number. We consider 1000 samples and our vocabulary size is 10. The proposed method outperforms the competition most of the time, but the differences are small overall. The same pattern is observed between 7 and 10 atomic propositions as well. Since these results are not conclusive, we prepared another experiment to evaluate this metric in a more isolated manner. This experiment is called the Perturbation Experiment. The basic idea here is that we introduce a bias to the training dataset. In particular, we transform the sample such that the order by which the propositions appear in the output is always the same. Since this is an alpha conversion, the model ideally should not get affected from this. We don't test generalization in this experiment since the purpose is to evaluate alpha covariance in a more isolated manner. Here are the results. As expected, the performance of the baseline model crashes when the training dataset is perturbed. On the other hand, the proposed method and alpha renaming baseline are unaffected by the perturbation. Therefore, we only display the perturbed results for these models. Both of these methods outperform the normal baseline in terms of alpha covariance even if the training dataset is perturbed. But alpha renaming baseline is slightly better than the proposed method this time in terms of correctness. The best model is the normal baseline, followed by the alpha renaming and then the proposed method. This ranking is the opposite of the ranking in generalization experiment. What we observe here is bias variance trade-off. Increasing the out-of-distribution performance decreases the in-distribution performance. But this decrease is much smaller than the increase in out-of-distribution performance. We also have the results from the Llama 3.2 here, but once again it fails. That was the end of the experiments. In conclusion, the advantages of the proposed method are as follows. Firstly, it introduces a favorable inductive bias for alpha equivalence. Secondly, it allows generalization to larger vocabularies after training. But as we have seen in the previous experiment, these advantages come at a cost. In particular, bias variance trade-off is still present. in distribution performance decreases slightly. Finally, this method is not directly applicable to natural language. For example, programming languages exhibit the concept of alpha-equivalence, but they also feature human-written variable names. Enforcing alpha-equivalence in such settings is not explored. That concludes this presentation. Thank you for listening.